Hydrogen is the lightest element in the universe, but storing it safely is one of humanity's greatest engineering challenges. Instead of compressing it into high-pressure tanks, we can now hide hydrogen directly inside solid metal. Today, we look at the invisible engineering making solid-state hydrogen storage possible. These are not ordinary pieces of metal. They are highly engineered alloys structured to absorb hydrogen directly into their atomic framework. This solid-state method eliminates the need for extreme pressures, creating a safe, highly compact, and remarkably efficient storage system that lasts for thousands of cycles. Deep within the crystal lattice of the metal, billions of atoms form a repeating three-dimensional framework. Between these atoms lie tiny, microscopic spaces called interstitial sites. For hydrogen, these empty spaces become the perfect stable environment to form secure chemical bonds. From the outside, the containment system looks like a standard pressure vessel. Inside, however, thousands of metal hydride particles wait. As hydrogen gas flows in at relatively low pressure, it avoids compression and begins safely disappearing into the dense, solid material itself. This entire process is completely reversible. The hydrogen enters the alloy, remains locked in place for as long as necessary, and can be fully released whenever energy is demanded. This highly repeatable cycle functions thousands of times without degrading the underlying metal. The journey begins as high-purity hydrogen gas enters the storage system under tightly regulated conditions. At this initial stage, the gas still exists as standard diatomic molecules, ready to undergo a profound chemical transformation at the surface of the alloy. As the hydrogen molecules make contact with the engineered alloy surface, a catalytic reaction occurs. The chemical bonds holding the gas together break, splitting the molecules into individual hydrogen atoms. These independent atoms are now prepared to migrate deeper into the metal. One by one, the separated hydrogen atoms diffuse into the crystal structure of the host metal. They find and occupy the vacant interstitial sites, bonding tightly with the surrounding metal atoms. The material remains entirely solid, yet it now contains incredibly dense energy. When the system is called upon to deliver energy, the mechanism reverses. By applying controlled thermal energy or modifying the internal pressure, we trigger the release process. The hydrogen atoms break their atomic bonds and begin migrating back toward the surface. Reaching the surface, the individual atoms seamlessly recombine into stable gas molecules. This engineered release produces a clean, high-purity stream of hydrogen gas, flowing out of the system at a steady rate, fully prepared for immediate use in downstream applications. Managing this atomic chemistry requires a highly integrated engineering system. By balancing precise temperature and pressure controls, the system ensures that absorption and desorption happen at peak efficiency. This balance maximizes storage capacity while maintaining absolute safety and operational reliability. This comprehensive cycle bridges the gap between raw hydrogen gas and practical clean energy applications. From power generation and industrial manufacturing to zero-emission transportation, the system provides a scalable, stable foundation for integrating hydrogen into our global energy infrastructure. Precise control instrumentation tracks the environment inside the reactor continuously. Maintaining specific thresholds, such as a steady operating temperature and low operational pressure, guarantees that the interaction between the gas and the metallic crystal remains perfectly stable and highly efficient. Unlike standard chemical batteries that suffer from gradual energy dissipation over time, metal hydrides retain their stored hydrogen indefinitely. The energy rests quietly within the atomic matrix, completely stable, waiting until the exact moment it is needed for power. Initiating the release phase requires a deliberate shift in the system's thermal dynamics. Introducing heat breaks the strong atomic bonds within the matrix, allowing the trapped hydrogen to escape its solid-state host and transition back into a mobile, usable gas. As the hydrogen atoms exit the metal structure, they automatically reform into pure gaseous molecules. This seamless transition ensures that the gas leaving the system is completely free of contaminants, maintaining the high purity required for sensitive energy systems. The purified hydrogen now moves directly into a fuel cell stack. Here, the chemical journey reaches its ultimate purpose. Rather than burning the gas, the fuel cell utilizes an electrochemical process to extract power, generating clean electricity with zero carbon emissions. Inside the fuel cell, hydrogen combines with oxygen from the ambient air. This reaction generates a consistent flow of electrical power and heat, leaving behind nothing but pure water as a byproduct. It is a highly efficient, entirely sustainable energy conversion cycle. Once the stored hydrogen is depleted, the containment system is ready to be recharged. Pumping new hydrogen into the system restarts the exothermic absorption process, packing the metal lattice with atoms once again and preparing the module for its next operational cycle. This remarkable atomic transformation alters the material itself, causing a slight expansion of the crystal lattice as it fills with hydrogen. By locking the gas into a solid state, we eliminate the need for dangerous high-pressure tanks, while guaranteeing an exceptionally long operational lifespan. Material scientists utilize several distinct alloy families to optimize performance. From classic combinations to complex formulations and lightweight magnesium-based systems, each distinct metallic structure is specifically engineered to satisfy different temperature, pressure, and weight requirements across diverse industrial applications. Designing these storage systems requires balancing critical engineering trade-offs. Some alloys provide massive storage capacity but require higher temperatures, while others offer rapid charge rates at room temperature. Matching the right material kinetics with the specific application is essential for optimal system design. Despite these trade-offs, metal hydrides deliver unparalleled advantages for modern energy infrastructure. They offer unmatched safety, high volumetric density, exceptional durability over thousands of cycles, and a reliable method to store clean energy without the risks of conventional gas compression. The entire process represents a masterclass in chemical engineering. From gas molecules splitting into individual atoms, resting securely inside a solid metal framework, and recombining on demand, this hidden journey provides a seamless, safe path toward a reliable, sustainable hydrogen economy. The future of clean energy relies on advanced, hidden infrastructure like metal hydrides. Understanding these systems helps us unlock the true potential of sustainable power. To explore the deep engineering driving modern energy solutions, join us at H2 Hub by Renewable, where every system shapes our world.